Hello, and welcome to another episode of Maths in an Empty Classroom with me, Mr. Southern. This is part one of the lesson on connected particles, and in this video I'm going to be going through an example of a car towing a trailer. So here we have lots and lots of information. A car of mass 800 kilograms is towing a trailer of mass 200 kilograms along a straight horizontal road by means of a light inextensible tow bar which is parallel to the road. The resistances to motion of the car and the trailer are assumed to be constant and of magnitude 200 newtons and 60 newtons respectively. The car's engine exerts a driving force of 5,000 newtons. So let's just underline the key information here then. We've got a car of mass 800 kilograms, we've got a trailer of mass 200 kilograms, connected by a light and extensible tow bar. So let's start off by drawing a picture of that. So we've got a trailer and we've got a car connected by a tow bar, and the mass of the car was 800 kilograms and the mass of the trailer was 200 kilograms. So I'm just going to write 800 kilograms in here and 200 kilograms in here to denote those masses of the car and the trailer. The resistances to motion of the car and the trailer are assumed to be constant and of magnitude 200 newtons and 60 newtons respectively. So I'm just going to add those forces to my diagram. So I've got a 200 newton force resisting the car and a 60 newton force resisting the trailer, constant in magnitude, so they're not going to change. And it says the car's engine exerts a driving force of 5,000 newtons. So let's add that to the diagram as well. Driving force of 5,000 newtons. What I'll also add is an acceleration or a direction of motion arrow to show that the car and the trailer are travelling in this direction because the car is pulling the trailer. And then just check the information. Car's engine says a driving force of 5,000 newtons. Find the acceleration of the car and the trailer. Now, there are just a couple of forces on here that I have not yet labelled. There is a tension force in the tow bar that resists the motion of the car because the car is connected to the trailer and that tow bar is pulling the car back because of the trailer being connected to it. Similarly, there is a tension in the tow bar here, and it is that force that is causing the trailer to move. So this 5,000 newton force is causing the car to move. That is then creating a force in the tow bar, and it is the tow bar that's pulling the trailer along. And that's going to be important when we come to consider separate particles later. But to start off with, we're looking for the acceleration of the car and the trailer. Now that is going to be the same for both particles because they're connected by a light and extensible tow bar. One of the modelling assumptions is that that system accelerates at a single rate. So what I can do for part A is resolve for the whole system. Using resultant force equals mass times acceleration. And I need to consider all the forces acting in the direction of motion minus all the forces opposing the motion. So acting in the direction of motion, I've got that 5,000 newtons, which is the driving force of the car. That is being resisted by the 200 newton force resisting the car and the 60 newton force resisting the trailer. I do not consider at this stage the two tensions because they are acting in opposite directions, cancelling each other out. And that is going to equal the mass. Now that's the total mass of the whole system, so that's 1,000 multiplied by the acceleration. Working out the left-hand side, I've got 5,000, take away 200, take away 60, which is 4,740. And that is equal to 1,000 A. So the value of A is 4.74 ms to the minus 2 metres per second. And that is the acceleration of both the car and the trailer because it's the same for both particles. Great, so it's part A. And part B is saying the magnitude of the tension in the tow bar. Now, we've got options here. We could resolve for just the trailer, or we could resolve for just the car. Now I'm going to do it for just the trailer because there's fewer forces acting here. So resolving for the trailer, again I'm going to do resultant force equals mass times acceleration, and now I only need to consider the forces that are acting on the trailer. So in the positive direction, that's this tension, and in the negative direction opposing the motion, it's the 60 Newton resistance force. And that is equal to the mass of just the trailer, so 200, multiplied by acceleration, which we now know from part A is 4.74. So if I multiply 200 by 4.74 and add on 60, I get the tension in the tow bar to be 1008 newtons. And that would also be this tension here. And what you might like to do to check is to set up an resultant force equation for the car. Check that you get the same value for T when you use 4.74 as the acceleration. Right, we've got some new information for part C, so let's read it and take note. The car is moving along the road when the driver sees a hazard. He reduces the driving force to 0 and applies the brakes, which produce a force on the car of magnitude x newtons, causing the car and the trailer to decelerate. Given that the resistances to motion are unchanged and the magnitude of the thrust in the tow bar is 180 newtons, find the value of x. Now, I would say new scenario, new system, new diagram. So I'm going to draw a whole new diagram for part C, because even though it's going to look almost identical, the forces have changed significantly. So I have my trailer, I have my car, I have my tow bar. So first of all, let's consider what hasn't changed. The trailer is still 200 kilograms, the car is still 800 kilograms, and we were told that the resistances to motion were unchanged. So we still have a 200 Newton force acting on the car this way, and we still have a 60 Newton force acting on the trailer this way. But now let's look at what's different. The driver has reduced the driving force to 0 and has applied the brakes, producing a magnitude x newtons, causing the car and the trailer to decelerate. Now this braking force is making the system decelerate, so it's acting in this direction. It is slowing down the system, so x is acting that way. Now let's just consider for a minute what's going to happen in the tow bar when we start to decelerate. If you're pulling something along behind you like so and you suddenly decelerate, you're going to feel a force like so. And that force is thrust. And the thrust in the tow bar is going to go into the car like this, and it's going to go this way into the trailer, because if you're being pulled by that tow bar and the system suddenly decelerates, you're going to feel that. And that's what's going on with this trailer here. So this is the thrust in the tow bar, which we're told in the information given is 180 newtons. So the crucial point here is that thrust is going in the opposite direction to tension. So we have 180 newtons here and 180 newtons here. And that is all the information that I have on my system. Now I'm being asked to find the value of x. So I'm either going to have to, I've got options here, I could set up a whole system, or I could consider each particle individually. Now the issue that I've got with whole system is, in addition to not knowing x, I don't know the acceleration either. So I can't do whole system. Same issue for the car, because I've got two unknowns, so I'm going to have to look at just the trailer. And the reason that I can look at just the trailer is that when I do my resultant force equals mass times acceleration, the forces acting on the trailer are both known forces. However, because the car and the trailer are still moving this way in the positive direction, both these two forces are going to be negative. So negative 60 minus 180 equals the mass of just the trailer multiplied by the new acceleration. So negative 240 equals 200A, which means that A is negative 1.2 ms to the minus 2. Now that should make sense. We've got a negative answer for acceleration, which makes sense because the system is now decelerating because of this braking force. So what I'm now going to do, now that I know A, the acceleration, I'm going to set up a resultant force equation for just the car. So resultant force equals mass times by acceleration. Now in the positive direction, the direction of motion, which is this way, I've got this 180 Newton force here, so that's a positive. But the other two forces are in the negative direction. So we've got minus 200 and minus x. Both those forces are going that way. Equals mass. Now this is mass of just the car, multiplied by the acceleration, which is negative 1.2. And it's very important we use that negative there because the system is decelerating. So what we have from here then, on the left-hand side, we have negative 20 minus x equals 800 times by negative 1.2, which is going to be negative 960. Just check that. Yeah. So adding on the 20, negative x is going to equal negative 940, which means that x, the braking force, is 940 newtons. So 940 newton braking force caused the system to decelerate at 1.2 meters per second. Now, if you're in a situation where you did this first, all that would happen is you wouldn't have known x and you wouldn't have known a. So you pause, and then you do just for the trailer to find A, and then you put that information in here. So if you start off with the wrong equation, it doesn't matter as long as you realise what you need and then set up another one to find it. Okay. I'll see you in the next video where we'll look at two particles connected over a pulley. I'll see you then.